All right, so here we go with part 2 of section 3.8. We're going to do an example of what is this? Newton's method. All right, so our first example is, and they gave us our initial x value here, so that's nice. But starting with a first value for x of 2, find the third approximation, that is x sub 3. So when we talk about approximations and we talk about this approximation or that approximation, the third approximation means x sub 3. The ninth approximation would mean x sub 9, right? And we're supposed to find the third approximation to the root of the equation, x cubed minus 2x minus 5. So now remember, a root is when a function is equal to 0. So finding the root is the same as finding the 0, is the same as finding the x-intercept, okay? All right, so first things first. Newton's method does not solve equations. What Newton's method does is finds when a function is equal to 0. So what is the function we're working with here? We are working with the function x cubed minus 2x minus 5, and we want to find out when f of c is equal to 0. Our job is to solve for c, okay? But I can't, because algebra fails me. I don't know of any convenient way to solve a cubic equation by hand, right? And since I can't solve it by hand, I'm going to use an approximation technique. The approximation technique that I'm going to use is Newton's method. Newton's method says start somewhere. In this case, we are going to start at 2, and then find all the next values in the sequence, x sub n plus 1, by taking the previous minus the function value at the previous divided by the derivative at the previous. Okay? Now, I already know f of x. It's right there, so I'm good with that numerator. But I do not yet know the derivative, so I'm going to need that. So if that's f, what's f prime look like? Well, f prime is going to be 3x squared minus 2x. Okay? So that tells me that x sub n plus 1 is going to be equal to x sub n minus, wait, let me move this down a little bit so I make sure I have enough room. X sub n plus 1 is going to be equal to x sub n minus x sub n cubed minus 2 times x sub n minus 5 divided by 3 times x sub n squared minus 2 times x sub n. And we're supposed to find the third approximation. We already have the first approximation, so let's go ahead and find that second approximation. X sub 2 is going to be equal to x sub 1 minus x sub 1 cubed minus 2 times x sub 1 minus 5 divided by 3 times x sub 1 squared minus 2 times x sub 1. So x sub 2 is going to equal 2 minus 2 cubed minus 2 times 2 minus 5 divided by 3 times 2 squared minus 2 times 2. You know what? I made a mistake with my derivative, didn't I? That's just 2. That doesn't belong there, that doesn't belong there, and that doesn't belong there. I knew something fell off. Okay, that feels much better. Now I just need to grind out a whole bunch of arithmetic here. So x sub 2 is equal to 2 minus 2 cubed is 8 minus 4 minus 5 divided by 12 minus, so divided by 10. So we've got, what is that going to be? 2 plus 1/10, or 21/10. So there's my x sub 2. But I'm not done yet. I need to find x sub 3. So x sub 3, right, let me change colors since I'm doing something new. X sub 3 is going to be equal to x sub 2 minus f of x sub 2 divided by f prime of x sub 2. So x sub 3 is going to be equal to 21/10 minus 21/10 cubed minus 2 times 21/10 minus 5 over 3 times 21/10 squared minus 2. So x sub 3 is equal to 21/10 minus, and here's where it's going to start to get ugly. I'm going to need a calculator for this. Let's see. 21 cubed is 9261. So 9261 over 10 cubed is 1,000. Minus 2 times 21/10 is going to be 21 fifths minus 5 over 3 times 21 squared is 441 over 100 minus 2. Okay, so then x sub 3 is equal to 21/10 minus, let's see, 9261 divided by 1,000 minus 21 divided by 5 minus 5 is 61 over 1,000. 3 times 441 divided by 100 minus 2 is 1123 over 100. 61 over 1,000 divided by, and so I get that x sub 3 is 21/10 minus, let's see, when I flip and multiply, that's going to cancel. 1123 over 610. I'm sorry, no. I got that upside down. It should be 61 over 11230. Yeah, that's right. And so then 21 divided by 10 minus that, and I get x sub 3 is equal to 11761 over 5615, or approximately 2.09. Okay, I'm going to pause this for a second. Okay, so I get that 2.09. If you really want to know on the calculator, it goes after that 4, 5, 6, 8, and it keeps going from there. So I don't know. How do I feel about this? I'm not sure because this is my first one. Did I get it right? I think I did everything correctly, but I got to admit that in here, things got a little ugly with those fractions. So what does Desmos say? Well, Desmos says 2.095. Looks like I got it right. So now your question, I'm sure that someone's asking, is why do I care about this if Desmos can do it for me? Well, somebody programmed Desmos. Someone programmed that in there to do this. How did they program it? Right? And so they were using something related to or similar to Newton's method. It's an iterative process. Now, the other nice thing about Newton's method is because it is essentially a loop, it's really easy to program it. So let's take a look at doing this exact same problem on my calculator. So first things first, I'm going to go to my y editor, and in y1 I'm going to put in the original function. So that was x cubed minus 2x minus 5. And then in y2 I'm going to put in that derivative. So 3x squared minus 2. And then what I'm going to do is I'm going to quit out of there and go back to my home screen. And I'm going to take the initial value, the initial starting value that we used here for our x sub 1, and I'm going to store that into x. Now, if you're wondering how I did that, lower left-hand side, you see the button that says STO? Stored, and then I press the X button. And so I'm putting that into the memory. Now, every time the calculator sees x, until it changes, it's going to think that x is 2. So it's just going to have that value of 2. Now, don't be concerned. This is not going to mess up your calculator's ability to graph. It's just for when you're in the calculator mode. It's stored in a memory location. Now what I'm going to do is I am going to type in this formula. Okay, not the left-hand side, but just the right-hand side of that. I'm going to take the x minus the function, that was y1. So y1 of x, and divide that by y2 of x. And then I'm going to store that value back into x. And what that line is essentially going to do is it's going to calculate Newton's method, get an answer, and plug that back into x. And it got 2.1, which was our first approximation. Not technically the second approximation, but it was the first one that we calculated. Was that what I meant by that? It's x sub 2. And now if I press enter again, it's going to give me x sub 3. The 2.094. And then if I press enter again, that would be x sub 4. Now I want you to take a look at those two values. And you see how they are the same tenths place, 0, the same hundredths place, 9, the same thousandths place, 4, the same 10,000ths place, 5, different hundred thousandths place. So they differ out at hundred thousandths. So we have accuracy out to 10 thousandths place. With 3 iterations of this, we have accuracy to 10 thousandths place. That was fast. And if I were to press enter again, you'll see that I have as much accuracy as my calculator can display. So what is that? Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions, 10 million, 100 millions, billions. We have billionths place accuracy. Is that accurate enough for you? Right? If not, we could do this by hand and keep going. Right? Now, another thing to keep in mind, you might be looking at this going, man, but that's troubling math right there. Well, it wasn't pretty, but it was nothing that couldn't be done by hand if you had nothing else to do with your day. So think back to when these guys were doing this in the 1800s, and they didn't have anything else to do all day. There was no Facebook, there was no Twitter, there was no TikTok videos to watch. And so what would they do? Well, they would sit around and they would have all day to find the root of this equation. So the fact that the numbers got bad, well, it was a way to find an approximation that couldn't be solved any other way, so it was as good as they could do. And so they liked it. It was good. Okay. All right. I'm going to end this video here, come back, do another example. Hopefully the next one will go a little faster. 15 minutes for one problem just seems like a lot. I'll see you back here for part 3.